Today we're going to start our exploration of refraction. And refraction is a very common phenomenon, and it's going to help us understand things like why we see rainbows and why the sky is blue and why we see different color sunsets and sunrises. So it's a pretty interesting topic. But first, let's see if we can get some of the basics down. So refraction is the bending of light when light goes from one material to another. So the bending of light when light goes from one material to another. And we see this happen all the time. You've probably looked at light when it enters through a window. So light has gone from traveling through a gas, the air, through the glass made up of the window, then through the air again as it gets to your eye. And we've talked about a couple different things what can happen when light hits a material. We've talked about how it can be absorbed, right? So when we talked about a green leaf, we said a lot of the colors of the light were absorbed, so that energy is absorbed, thus heating up the leaf. We've talked about how light can also be reflected, right? That's why we see the leaf to be green, because all of the green light is reflected to our eye. And now we're going to see that light can also be transmitted through. So with a window, of course, it's very common for light to go through the glass, but when it does, it actually gets refracted, so it changes speed. Okay, so kind of another way to phrase refraction is the changing direction of light. Okay. Due to the light entering a new medium. And the new medium has what we're going to call a different optical density. Okay, different optical density. All right, what does that mean? We talked about sound, and we said that sound actually has a constant velocity in air as long as the temperature of the air doesn't change. We're going to see that's the case with light as well. But when sound travels through a liquid, it travels faster. When it travels through a solid, it goes even faster. Light is going to be different, and it's actually going to be the opposite. Light is going to travel really well through the vacuum, like a vacuum of space, or through a gas like air. It's going to slow down when it hits a liquid like water, and it's going to go even slower when it hits a solid like glass or even diamond. So let's get some of that into our notes. Okay, so light in a vacuum has a constant speed. And in case you don't remember, that velocity is 3 times 10 to the 8th meters per second. Not a big deal if you don't remember that one. But when it changes mediums, it changes speed. Okay, so when light changes medium, it changes speed. Okay, mediums that are optically denser have a slower speed of light. Now, why does this happen? We're gonna watch some videos and we're gonna use some analogies. But basically, this has to do with the fact that light is a wave. Okay, so we have to remember that light is a wave. And when the wave front hits the new medium, that's when the bending occurs. So think about if you've ever cut your grass or if you vacuum. We'll use the cut the grass scenario. So if you're cutting your grass and you've got your lawnmower and it's heading straight on into the grass, you know when the two front tires hit the grass, you know that the lawnmower is going to go slower. than when it was on the driveway or on the sidewalk. Now, imagine this way. So those two front tires are like the wavefront. Now, if you set up your lawnmower so that you're mowing at an angle, right? Some people do that. They like to mow their lawn. It looks really nice when you mow at that angle. When you do that and you're on the driveway, one of the wheels on the lawnmower is going to hit the grass first, and it's going to go slower than the wheel that is still on the driveway. When that happens, it starts pulling the lawnmower in a different direction. And now, because that second wheel hasn't slowed down yet, you're getting one wheel going slower, one wheel going faster, and it turns. So that's exactly what happens to light. The light wave hits the boundary, and if it's at an angle to the boundary, we know the light wave is going to turn. Now, you're fine if you're going straight at the boundary, then you're fine. The lawnmower still will slow down, but it won't turn. So we're going to see that with light as well. So fast to slow speeds in materials, we're going to see that a vacuum is the fastest, okay? It's very easy for light to go through a vacuum because it's not running into anything. There's nothing for it to run into and slow down. We're going to see that air is very fast. We're going to see that water is a little slower than air, but that glass is even slower than water. And when we're looking at something really slow, we're going to get diamond. And we're going to see that that's why diamond sparkle. We're going to talk about that when we get a little further down on our notes, okay? So we're going to have to measure some angles, and we're going to get some ideas of how light bends. So the first thing we're going to do is we're going to go ahead and we're going to draw a boundary line. And you guys on Notability are going to be able to do this a little better than I. But there's my boundary line. So down here, I might have, say, water. And up here, I might have air. And this is the boundary between the two. So I'll have a light wave hitting, and I'm just going to draw the light wave, even though it's a wave. I'm going to draw it as a ray. We're used to drawing as ray now. We did that with our mirror investigation notes. So I've got the light is going to hit the boundary. Just one ray is going to hit the boundary there. And what I want to do is I want to go ahead and draw a perpendicular to the boundary right where that incident ray hits. Remember, the light that's coming in, and we did this with our mirrors too, this is going to be called the incident ray. Now, if this is really the boundary between air and water, we could get some reflection as well, but we'll talk about that later. But most of the light is going to go through the water, and it's going to bend, okay? And when it bends, we're going to see something like this. We're going to see that light, and it's going to bend this way. We'll talk about why that is in a little bit, okay? Now, let's go ahead and let's take a look at, because people struggle with this, let's take a look and see what if the boundary isn't that horizontal line? What if it's a vertical line right there? That's okay, so this is the boundary now. And the light, let's say the light is coming in like this. Then our perpendicular, remember, we're going to say that our perpendicular is always perpendicular to the boundary. It's going to look like that, okay? And that's going to be our normal line. And I didn't put that over here, so let's put our normal line. And then we're going to have some angles that we're going to be measuring as well. And this is going to be a little different than how we did this with our mirror, because we're always going to measure our angles between the ray, so in this case the incident ray, and the perpendicular. So this angle right here would be our theta I. For our second picture, this angle right here would be theta I. Now, we could also have a boundary that's not horizontal, that's not vertical. We could have it at some weird angle. We could have it coming in like this. And then maybe our incident ray is coming in like this. So we would have to draw a perpendicular, but that's just still a 90-degree line. So I'm going to draw it like this. That green line is now perpendicular to that blue line, the line segment without the little arrow. And then hopefully you can see that my incident angle is this angle right here. And if we did one more example, we could draw our boundary like this. We could go ahead, we could say, well, here's our incident ray. We would have to draw our perpendicular like this. And then we would see that this angle right here is our incident angle. So our green lines here are our normal lines. And the blue lines here are always our boundary. Now you can use any colors you like, but I'll try and stick with those, that kind of convention for our notes for today, okay? Now, we know that we're going to get some bending. And we're going to kind of break this up. There's a way, we're going to watch a video and they're going to talk about Snell's law. And there's a way to figure out exactly how much the light ray is going to bend depending on the angle that it's hitting the boundary at. But we're just going to take some generalizations first. And we're going to go ahead and we're going to draw a boundary. We'll just draw it horizontal, okay? And we're going to say that this is water down here and this is air up here. And we're going to have our incoming light ray. And I'm just going to draw it like that with my arrow up there. So we know we'd have to draw a normal line. And then I could go ahead and label my angle. This is my theta incident, okay? Now, the key for this is knowing that when we're going from a fast medium to a slow medium, in this case I am, because I know air is faster than water. So we talked up here about how the speed of light changes in different materials. I know the vacuum is the fastest, then air, then water, then glass, then diamond. So it's really just, nothing, right? Nothing in the, really no medium, to the least dense, a little bit more, a little bit more, a little bit, very much more dense, okay? So we're just kind of looking at density. That's what we're going to follow for our optical density. So in that case, what we're going to have to remember is that when we're going from a fast to a slow medium, the light is going to bend towards the normal line. And the way I remember that is I remember F-A-S-T. So what that means is when I'm going from a fast medium to a slow medium, the light bends towards the normal. So what does that look like? That looks like this. The light bends in that direction. If it hadn't bent, and don't draw this one, if it hadn't bent towards the normal, it would just go straight through like that. But that's not what's going to happen. Okay, so since that's not what's going to happen, I'm going to go ahead and I'm going to get that for and I'm going to call that my refracted ray, and this is going to be my theta r, or my refracted angle. Remember, we're going to measure our angles between the normal line and the light ray. So when I'm going from a fast medium to a slow medium, we're going to bend towards the normal. So that's how I remember that, F-A-S-T, okay? Now, when I'm going from slow to fast, we have the opposite occur. We're going to see that we're going to get our light to bend away from the normal. So away from the normal. And I remember SOFA, S-O, which you don't really need F-A. So again, we're going to go ahead, we're going to draw our boundary. And this time, this is going to be the water up here. This is going to be the air down here. We're going to go ahead, we're going to have our light ray hitting. Once the light ray hits the boundary, we know where to put our normal line. We know how to draw it. We know that this is going to be our theta I right here. And then since I'm going from a slow medium to a fast medium, I know the light is bending away from the normal line. So that right there is going to be my refracted ray, and this is going to be my refracted angle. So you can see here that my refracted angle is going to be greater than my incident angle. Whereas over on the fast to slow side, I know that the refracted angle is going to be less than the incident angle. Now, to know how much less, we'd have to know something about the air or the water, and we'd have to have an equation. We'd have to use Snell's law, which if you watch some videos, and I am going to have you look at some videos, they'll talk about Snell's law, but we're never going to have to use the math. We're not going to do those calculations. So for right now, just worry about kind of the idea of which way does the light bend, all right? Now, here's a pretty common example of refraction. We have a glass. and the glass is partially filled with water. And in the glass we put a pencil. And there's a couple things you should notice about this pencil. One is that the pencil in the water looks bigger than the pencil outside of the water. Right? It looks a lot bigger, kind of like we're holding up a magnifying glass. Two is that it looks like the pencil is broken right at the surface of the water. It looks like the pencil is either curved or it's moving in a different direction. It looks like it's bent, right? So that's a typical sight that we'll see when we're talking about refraction. And we're going to get an idea of how this occurs, okay? But for right now, just realize that this entire phenomenon right here, this idea that right at the surface we've got this breakage of the pencil, this entire phenomenon is explained with refraction. So when we look at those pencils, the question here asks, well, why does the pencil look bent or even broken? Give evidence. Well, the simple one-word answer is refraction. We want to do better than that. We know that the light bends, and because it bends, it appears to be coming to our eyes from a different location. So think back to when we first started studying flat mirrors. And we said, well, when we look at in a flat mirror, we're looking at an image, right? We can't actually see our face. We can see an image of our face. And that image appears to be coming from behind the mirror. And we said, well, the reason, right, that the image looks small, because we know the image is the same size as the object when we look in a flat mirror. The reason the image looks small is because it's farther away. And we talked about how the houses across the street look really, really small. They're not. They're regular sized houses, but they look really small because they're so far away. Well, with refraction, with the pencil in the glass, we have the opposite happening. We're looking at the pencil, and the image of the pencil is really what we're seeing when it's in the water. The image of the pencil is actually closer than the actual pencil, so it looks bigger. And that's exactly what we have here. So give evidence to back up our answer. Well, we know it's the same pencil, but since the image looks closer, than the object, we must have light bending and coming from a or at least appearing to come from a place that is not the same as the object. And we'll kind of do some drawings that'll help us out with that as well, okay? Now, let's take a look, and we're going to draw a couple more pictures here. Let's take a look and see what happens when we have light going from water to air again. When we have that happening, sometimes it occurs at a small angle. So we can draw and we can say, okay, that's a pretty small angle that we've got here. So theta I is pretty small. And we know we're going to get some bending away from the normal. So we're going to get something like that. But then as we change that angle, so let's make that a bit of a bigger angle now. Right, so the light is still going to bend and it's going to be kind of like this now. But eventually we get to a point where the light comes in at such an angle, and we still have our normal line here, that when it refracts, when it bends, it's basically bending, wrong color. It's basically bending right along the surface. And we give that a name. So if we call these, this is our theta I, this is our theta I. Right here, we're going to say that theta I is equal to a critical angle. And we're going to define that, okay? We're going to define that. The critical angle is the theta I that causes theta R to equal 90 degrees. So this angle right here is 9, and it's hard to draw, right? Because the colors I've chosen. But this angle right here, theta r, is 90 degrees. So theta critical is the theta I that causes theta r to be 90 degrees. Well, anything bigger than that, okay, if theta I is greater than the critical angle, what's going to happen? And we're going to see that right down here. We're going to see that when that occurs, we don't get refraction anymore, we get reflection. Now in reality, in all of these situations, we're going to be getting a little bit of reflection. So even over here, when we have a pretty small theta I, you're going to get a little bit of light, just a little bit, that's going to reflect off. A small amount. That's why when you're looking outside a window, so maybe it's daytime out right now and you're looking outside the window, you don't see a reflection, because that light is being overwhelmed by the light that's coming in from the outside. But maybe when you are in the dark at night sometime, look out a window and you might see the reflection a little bit easier. You might be able to see the image of your face. Okay, so try that and you'll see that there is some light that's reflecting. However, when we reach the critical angle and we eventually exceed the critical angle, we're going to see that none of the light refracts anymore. It doesn't bend into the air. It all reflects. So total internal reflection occurs when all the light hitting a boundary reflects back into the original medium and none leaves. So all the light reaching a boundary reflects back into the original medium, or we can call it maybe the incident medium, and none escapes to the second medium. Okay. This occurs when the incident angle is greater than the critical angle. So if we take a look at our drawing here, and let's just label this. Let's say that this is the fast, so maybe this is the air, and this down here is the slow, maybe this is water. Now you might be asking, well, how do I know that? Well, I know that because if I were to go ahead and I were to draw a perpendicular right here, I would see that since the light is bending, if this is my theta I, if the light is bending towards the perpendicular, which it is in this case, it must be going from a fast medium to a slow medium. And I can see that no matter how big the angle is, my incident angle, when I'm going from fast to slow, I'm never going to get total internal reflection. But when we go over here and we start looking at some of these rays that are going the opposite directions. Now these rays are going from the water to the air, or from the slow to the fast. Now we can see a situation where, look what's happening. We've got this theta I, we've got theta r getting bigger and bigger right here. We would call this our critical angle, because this angle right here is 90 degrees. So the light is actually traveling along the boundary. And this angle right here, this internal incident angle rather, this angle must be greater than the critical angle, because now we're just getting reflection. So this angle right here is still a theta r, but it's a theta reflected now. It's not refracted anymore. This is a reflected angle. And whenever we reflect, we still, remember, it's a law of reflection. So the law of reflection still has to hold here. So the theta I has to equal the theta r as it's reflected. So just to answer a couple of these questions, if a light ray in a material strikes another material at the critical angle, then what is the angle of refraction? Well, we know that that's going to be 90 degrees. And of course, that's always measured from the normal. If the angle is less than the critical angle, then what happens to the light ray it strikes? Well, most of it's going to refract into the second material. Some of it will still reflect, but we're not going to worry about that. Okay, so it's going to refract into the second material. But if the angle of the incidence is greater than the critical angle, then all the light reflects and remains in the original material. And it must follow the law of reflection. So we could look at some critical angle values for when light is going, for instance, from water to air. So we know that this is the slow and this is the fast. And the critical angle, and you could Google this as well, is 48.6 degrees. Any incoming angle bigger than that from water to air, and we're going to get total internal reflection. For glass to air, it's 41.1 degrees. So more of the light is, there's more light that's more likely to undergo total internal reflection when we talk about light that's going from glass to air. From diamond to air, diamond is really, really slow. The critical angle is 24 degrees. That means that when light goes into a diamond, it's very hard for that light to escape. Okay, it's really hard for light to escape from a diamond. This is why they sparkle. Once the light gets in, it spends a lot of time bouncing around in the diamond before it can come out. So we see that sparkling going on, and that's why diamonds sparkle. Okay, so jewelers are very adept at cutting the diamond in such a way so that the light is trapped as much as possible, because people like that. That's when it sparkles like that, that's a good property for a diamond to have. So to answer this question, this last question, where is TR more likely, between water and air or between glass and air? We would have to say it's more likely in the glass, because the critical angle is smaller, so more of the light is going to get trapped. Okay? All right. If you look on our Canvas page or our Schoology page, depending on what you're looking at, you will see that we've got a couple other videos, at least one other video for you to watch, but hopefully this clears up some refraction questions, and we're going to do an activity going forward, and eventually we're going to start talking about rainbows and other atmospheric refraction. So thanks for listening.